All right, ladies and gentlemen, good morning or good afternoon, depending upon where we're at, what time of day you're looking at this, and welcome to part one of covalent bonding. I'm going to just look at this quick essential question. We're going to start simply and how we're going to look at how two atoms of the same element form a covalent bond. So this is how we're trying to figure this out. And this is right now just two, because this is the simplest way to how to do things. Looking at two atoms of the same element, how they come together, then we're going to take that and then move it forward in the next lecture to say how two atoms of different elements bond together, because that's slightly different. So let's use Lewis dot explanation to see how this works. So let's look at something very simple, and let's look at hydrogen. We have hydrogen here, and here's the other hydrogen. And a little farther away, we have two electrons. I'm using X to designate the electron on this side to make a difference. And now what's happening for this to occur, for bonding to occur, for sharing to occur, this electron on this hydrogen must be on the same side as where this hydrogen should be. So it has to be over, it can't be over here, it has to be here. And this hydrogen, this electron on this hydrogen has to be close to this one. And remember, there is, I'm going to draw this a circle, there's an empty space. So you can accept, hydrogen can accept another electron. And what happens is that this sees this open space and it wants to come over this way, and this comes this way, and they tend to bring the atom together. And actually, this happens by they collide. They don't. It's not just an attraction. They actually have to hit each other for this to work, and the electrons have to be on the same side, next to the atoms, and then we see that they come together and they pair up, and it looks something like this. This is a Lewis dot structure of H2, hydrogen molecule. And now, we don't usually write it like this because we're lazy and we like to draw a straight line. So a straight line is equal to two electrons that are shared between two atoms. And the reason we do use a line, because let's look at chlorine. Chlorine's the same way. We use dots on the left-hand side. It has an open space here, and here's chlorine, and we use X's on this side. Here's my X, and here's an opening. So here's our chlorine. Here's the spaces, and they're going to come together. Now, if we use dots and X's, or two dots, and we notice that this is a Lewis dot structure. And if you want to write it like this, you can, but ultimately we're going to see this as the official Lewis dot structure for the molecule. And actually, I'd rather just write it like this, knowing that there are electron pairs around chlorine, but they're not going. We don't see the structure, so we don't care about them at this point. So this is what I want you to look on the test. So this is how this works. Now, reiterate, covalent bonding is the sharing of two electrons, and the atomic orbitals must overlap for this to occur. And we're going to look at two ways of how they're going to overlap. And first thing, and we're going to look at S and P orbitals. So S orbital is my atom, let's go H, and let's go H. And these things are going to come together. They're going to go like this. The electrons are in this orbital, and the two atoms are going to come together and hit. And if their electrons are on this side, are here and here, and this is all probability, but as long as they're both on next to the atoms that they're going to be hitting, they're going to form a bond, and it's going to look something like this. And the two electrons are like this, and they form a bond, some energy is given off, and the molecule's happy. And we'll talk about how that works in a minute. For p orbitals, remember the p orbital, let's look at carbon. Just looking at this p orbital only, the electron has to be in this lobe and this lobe. When they collide, and these things are going to form a bond, and it's going to look something like this with a little thing at the end. All right, so this is we call this an s orbital or single bond, and we'll call it, and it's called sigma bond. And the sigma word, this is from the Greek, and this is the sigma. This is the Greek letter sigma. It comes from symmetry and what we call group theory. It's advanced type of mathematics for chemistry. Don't worry about how we got it. Just know that this is what we call a single bond, a sigma bond. So when one atomic orbital from each atom comes overlap, two molecular orbitals are formed. So two atoms, we've got two orbitals coming over from two different atoms overlapping, and we're going to form molecular orbitals. Two molecular orbitals are formed. So two are coming in, two have to come out. And they're called bonding and anti-bonding. Anti-bonding is designated by asterisks. And we'll show you how that works. So let's look at hydrogen coming in. So we usually have hydrogen, H2, and hydrogen. This is the energy diagram. So this is energy, if I can write straight. And here's my 1s, here's my 1s. Now H2 has a molecular orbital, and this is sigma, and this is sigma star. Now how this works, we have one electron here, and H2 is going to have two valence electrons. And this is how these diagrams work. So this is the first hydrogen, this is the second hydrogen, this is H2. We have two electrons. Using Hund's rule, using Aufbau principle, and the Pauli exclusion principles, we can fill all these up. And we'll talk more about that later. So anytime, even with the P's, and we'll show, actually we're going to show the P orbitals a little bit later. And I think I just ran faster. Of course I did. This is sigma bond, S and P. Then we get to the double and triple bonds, pi orbitals, side by side and merging together. And this is true. A single bond must be present for this to occur. You cannot have a double bond without a single bond. So what happens is that we have, let's say, carbon is going to form a double bond. We need to have this sigma bond first, and what happens, I'm going to draw this down. The atoms get closer together. So this is moving together, and to even make it closer, we have an electron in this one, electron in this one. They're actually going to fill an attraction because that's an empty space, because they need a pair. And so these kind of merge together, and we end up getting not only this as a drawing, but also this, where we have two electrons here, and we got an electron up here and an electron down here, or they can be both up here and both down here, because it all depends on how they're moving. Now let's look at the energy diagrams of how these things work for oxygen, and we're going to look at oxygen and nitrogen gas. So let's look at nitrogen, or let's look at oxygen. So using the Lewis dot structure, oxygen is this. And again, we're going to do it over here. Remember, there are two spaces. There's a space here and a space here that the oxygen wants to have an electron in there. Same thing over here. And what's going to happen is they're going to kind of cross or bond together and share. So we're going to see a double. Whoops. Let me get my eraser. That's red. I want blue. Well, that's magenta. Blue, 3, 4. And you notice that these are all correct, and this is a double bond, so we draw it like this. So we have a double bond. This is my double, here's my single. So this is what we mean by single bond must be present in order for this to occur. And this is why I usually have you guys draw the line first before pairing up, making more bonds. The single bond has to show up first. Now nitrogen is one of those. We've got 3 valence electrons. We've got 5 valence electrons present. And this is what drives students nuts, because when we get things like this and you're trying to pair them up, people hate doing this, but it is, all these connections become single lines, and we got a triple bond, 3 bonds in between the two nitrogens. How this works with energy diagrams. Let's go with O2, oxygen, O2, oxygen, and this is the one at, let me do some erasing a little bit. This is too low. One S, 2S, 2P. And now I'm just gonna draw these. This is not like I want it, but you'll get the idea. So we're taking 1, 2, 3, 4, 5, and we need to have 5 on this side, so we need 10 orbitals. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is my sigma, sigma, and sigma. These are all sigma bonds. These are all pi. I mean sigma star. These are my pi. This is my pi star. And this is my sigma star. And what happens is we got oxygen has 1. So they have 8. I know what it looks like, so I'm going a little bit faster on this. And so let's go ahead and put the 16 in there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So this is the energy diagram of O2. You notice that these kind of cancel each other out, so we don't worry about this, but we'll just worry about what's up here. This is how the energy diagram looks for pi orbital. These are side by side, and you notice we have 2 unpaired electrons, meaning that O2 is magnetic, which is true. So this is why we know that how this looks like is true. That this molecular diagram is actually a better picture than the Lewis dot structure, because the Lewis dot structure does not show that oxygen has an unpaired electron, while else the molecular orbitals do. And so this is how this looks like, and we're going to be using this diagrams later, and how we're going to talk about how things bond a little bit later and throughout the semester. So we're going to use energy diagrams. Remember, energy is increasing as we go up. Bear with me and ask questions about this, because it's conceptual. We need to have you understand the concepts of this. And this is what we mean by side-by-side interactions. So the energy split up. So we can actually have a triple bond. And this, if we look at nitrogen, whoops. If we look at nitrogen and 2, just look at the 2. This is the 2p, 1, 2, 3, 1, 2, 3, and we'll end up with this. And we're just going to end up with these folks, and this is true. I'm going to finish this up. We'll go into more energy diagrams later, but single bonds are long, double bonds are shorter, and triple bonds are shortest. And I'm running out of time. These are weak bonds because it takes less energy to break them totally. than the double bonds and triple bonds, which are the strongest. All right, I'm running out of time. Thank you guys, and I'll have another lecture later.